This is Inverse Relations and Functions, Chapter 6.7. We're going to look at inverse relations, inverse functions, and then possibly get into one-in-one functions. Inverse of functions. Explain what the net result is when a function is followed by its inverse. What happens, and then write an example. So what happens is basically these things, functions and inverses, are going to undo each other. For instance, if you have a square, then we square root. If we have a square root, then we square to undo it. If you have addition, we use subtraction. If we have subtraction, we use addition. Okay. So suppose function f converts number of feet to the number of inches. If we have 12x, okay, we're going to give us some order pairs. In other words, we're going to plug in some x values and see what the y's come out to be. So if we plug in 1 times 12 gives us 12. If we plug in 2, we should get 24. If you plug in 3, we should get 36. For the g of x, suppose the function g converts the number of inches to the number of feet. So we're flip-flopping around. Now we need to look at, well, how do we go from feet to inches? We multiply by 12. How do we go from inches to feet? We divide by 12. So this is 1/12 x. So if we take and we put in 12, we'll get 1. If we plug in 24, then we get 2. And if we plug in 36, we get 3. In essence, if you look at the two functions, the points on the left and the points on the right, really all we did was flip x and y. Okay, so our f and g inverses, the answer is yes. So what do we notice about them? We just took the points and x and y's are switched. For the domain, okay, so this is pretty much what we have here. All we do is flip them. The domain of the function is the range of its inverse. Here's my range, 1, 2, 3, and those are all the x values or the domain for the original function. So the range is then the opposite. The range is the domain of its inverse. Next thing, given the relation, so if we have 1, 2, 4, -2, 3, -2, is our function. Question is, well, if you remember, what do we look at? If we have points, we look at the x values. All of the x values, 1, 4, and 3, they're all different, so the answer is yes, it is a function. Now, we need to write the order pairs of the inverse, meaning r to the -1. Okay? Well, the relation to the -1, all we have to do is flip the points, and all we're going to do is, instead of writing 1, 2, we're going to switch them to 2, 1. Instead of 4, -2, we're going to write -2, 4, and then this will be 2, 3. If we actually look at this, note, r to the -1 is not 1 over r. So if you think back to that last little section, when we were doing x to the -2, it was 1 over x squared. Inverses, this is not related to that inverse. Okay? So not the same thing. So if we look at our inverse, is it a function? Well, we have a 2, we have a -2, and then again we have a 2, and they're different y's, so the answer is no. This inverse is not a function. Okay, so that's using points and looking at functions versus not a function. What if we graph it? Okay, if we sketch the graph of the inverse, hint, what we want to do is we're going to switch the x and y values to give us more points. So for the first one, if you notice, we have a couple points. So let's use -1, and that was about 1/2. 0's 1 is easy to see. 1, 2 is easy to see. And then 2, 4 is easy to see. Okay. So if we switch each of the x and the y's, you should get 1/2 -1, 1, 0, 1, 2, or 2, 1, and 4, 2. If we graph this, this is going to go up like this. This is going to go probably like that. So the domain for the original function is your -1, 0, 1, and 2. Okay. Our range is 1/2, 1, 2, and 4. Okay. When we look at the inverse function, we have now -1/2, 1, 2, and 4, and then -1, 0, 1, and 2. If we draw a line, well, can you look at the graph and look at the original function or look at the inverse? Is there anything that you can notice? Okay? And if you actually draw this line, what we call the y equals x, which is there, they are, you guessed it, they're mirror images. Functions are and their inverses are symmetric over the line. It's like a folding line, so they're mirror images of each other. Sketch the inverse. Is the inverse a function? Well, we need some points. So let's go with, so we know there's 0, 0. Okay, the far left looks like it's -2, 4. Looks like we have -1, 1. And then we have 1, 1. And we have 2, 4. So to get the inverse, we're going to flip those. We'll make this in green. Okay, now we have 0, 0 stays. We have now 4, -2. We have flipped the next one, the third one. Now you have 1, -1. We have 1, 1. And then we have 4, 2. So if we plot those on the graph, this is what we get. The green parabola or sideways parabola. Okay. If you remember, the vertical line test determines whether a relation is a function. So if we look at the first relation, the parabola that was going up and down, if we draw that vertical line, okay, we can draw essentially a vertical line anywhere through that parabola, and it was a function. So what line do you think will determine the inverse of a relation of a function? Dun, dun, dun. It is a horizontal line. So we need to draw a horizontal line before you actually graph the inverse. So for instance, if we draw the horizontal line in blue right here, if we draw a horizontal line through our function and it crosses twice, then the inverse is not going to be a function. So our blue line goes through the parabola twice, so the inverse is not a function. So we need to use the VLT to determine if the relation is a function, and the HLT to determine if the inverse of a relation is a function, and use a BLT if you're hungry. So these three graphs right here, we want to determine if the relation is a function and then if its inverse is a function. Take the first one. Okay, if we draw a vertical line test says it goes through it twice, so the answer is no. The relation is not a function. If we do a horizontal line test, there and so forth, you will say yes. So the inverse will be a function, not the original relation. So the relation, we can draw multiple here, so yes. But the inverse, if you notice right through here, the green, it goes through multiple times, so the inverse will be no. And the last one, draw vertical lines, yes. And horizontal lines, right here is going to be a troublesome part right at the 0, but the answer is yes. If we were to blow that up a little bit bigger. So what if we have now, so we started with points, then we looked at graphs and y equals x and mirror images. Now what do we do if we have equations? So we have f of x equals 2x minus 4, and we want the inverse of the function. Okay, quick side note. Notice how this says f negative 1 of x. Okay, this is not 1 over f of x. F of x negative 1. That is 1 over f of x. Okay, we are not doing the reciprocal. We are doing inverses. So the original equation, what we need to do, if we slide over to the right, we need to replace f of x with y. We're going to then switch wherever the x is, we're going to switch the x to the y and switch the y to an x. Okay, the third thing is we're going to solve for then now y, and then at the very end, wherever y is, we're going to replace the y with the new f negative 1 of x to call it the inverse. So number one, if we have y equals 2x minus 4, we're going to switch the x and the y. So this becomes now x equals 2y minus 4. Now you solve for y. Add the 4 over, divide by 2. By solving for y, we get y equals negative 1/2 x plus 2. We need to now switch the y with f negative 1 of x and make it 1/2 x plus. Go ahead, hit pause. Try number 2. Check back with me in a sec. Welcome back. Checking through the work. Hopefully you got f negative 1 of x equals negative 2x plus 4. So now we have points, graphing, and we just did an inverse. Okay, now we're looking at compositions and inverses. Okay, so going back to the number 1 we already know is 2x minus 4, and we just solved and got 1/2 x plus 2. Okay, those two equations we said were inverses. So we know that they're inverses. So if we use Fogg and Goff, or f of g and g of f, let's see what we get. So the original function, what we're going to do is we're going to take f and plug in the g function, and the g function was 1/2 x plus 2. So we're going to get equal to, we're going to get 2, we're going to get 2 times 1/2 x plus 2 minus 4. Simplifying, you're going to get x. If we jump over to the g of f of x, to the g function, we're going to plug in 2x minus 4. Okay, see what that's equal to. We get x. So when we did Fogg, f of g of x, and Goff, g of f of x, both equations were equal to x. So the following property of inverses is used to determine two functions are inverse or not. If Fogg and Goff equal x, then f and g are inverses. So the last problem. If we use properties of inverses to determine whether or not f of x and g of x are inverses, hit pause, do Fogg and Goff, and see if the two functions are inverses. Go. Welcome back. Because f of g of x is equal to x and g of f of x is equal to x, we can say that f and g are inverses. So that wraps up 6.7. We've looked at inverses. We can find inverses using points. We can find inverses using graphs. We can find inverses by using equations. And we can determine if two equations are inverses by using Fogg and Goff. Do your best, forget the rest. See ya!